In this video, we're going to explore the relationship of the concentration of reactants in a chemical reaction to the rate at which that reaction takes place. We know that increasing the concentration of reactants is going to cause an increase in the rate of a chemical reaction simply because of collision theory. The more reactants we have, the more collisions we're going to have, and the more chemical reactions are going to occur. We can define this relationship more specifically in a mathematical formula that we call a rate law, such as the one that we see here. We can see that the concentration of both of our reactants, A and B, in this case, appear as the most important and predominant part of the rate law, and we can see there is a direct relationship between the concentration of each and the reaction rate, meaning that if we increase A or B, it will directly increase the reaction rate. Now, we also see that there is K, which is a constant at the beginning of the rate law here, because concentration is not the only factor that influences the reaction rate. The other major variable that does is, of course, temperature. The higher the temperature, the higher the reaction rate is going to be. Now, K being constant assumes that our temperature is also going to be constant because, again, we want to separate the relationship of temperature and concentration. And it needs to be written separately because the concentration of either of our reactants is not going to affect the temperature, and therefore that's why it's written separately. Now, what isn't immediately obvious is the degree by which increasing A or B's concentration is going to have on our reaction rate. Let's say if we double the concentration of A, is that going to double our reaction rate? Or maybe it's going to increase our reaction rate 4 times. We don't actually know what this is. In order to account for this, we can assign 2 exponents, m and n, to represent the order of the reactants. Order, of course, being short for the order of magnitude. And the order of magnitude describes the specific relationship between how changing the concentration of our reactants can affect the reaction rate. This can only be determined through data that we get from an actual experiment. So here we can see in this decomposition of ethanol, we can see that we've changed the concentration by 0.1 moles per liter in every experiment, and this causes varying levels of increase in the rate of decomposition. So what we actually want to do is compare the results of 2 different experiments. In this case, we're going to use 1 and 2, and seeing what doubling the concentration is going to do to the reaction rate. And we can set it up like this. If we compare experiment 2 and divide it by experiment 1's results, we would see here that we have doubled the concentration here, and we can show this because 0.2 divided by 0.1 is equal to 2. Now, the exponent we want to solve for in this case, let's just call it m here. What we want to do is figure out what this exponent is by comparing it to the rates of decomposition. So if we take 0.34 moles per liter per second from experiment 2 and divide it by 0.085 moles per liter per second from experiment 1, this number, if you put this into your calculator, comes to 4. So again, if we want to figure out what our exponent or what our order of magnitude is for the concentration of our reactant, what exponent do we need to raise 2 by in order to get 4? Well, here we can see that m must equal 2, and therefore we can write our rate law as being rate is equal to K, which is our constant that represents the effective temperature, times the concentration of our 1 reactant here, which is ethanol, raised to the exponent 2. So what this means is that the concentration affects the reaction rate by two orders of magnitude. In other words, this isn't a direct linear relationship, it is a quadratic relationship. Now, the final part in rate law is to actually calculate what K is to show what the effective temperature is independent of concentration, and we can do that simply by taking data from our data table and plugging it into this equation. So if we were to take the data from experiment 1, we would say that our rate is 0.085 moles per liter per second is equal to K times our concentration of ethanol, which in this case is 0.10 moles per liter. And now that we have our order of magnitude here, we can put this exponent in, and algebraically, if we isolate K, this would mean that we would have 0.085 moles per liter per second divided by 0.10 squared. And if we put this into our calculator, this comes out to 8.5. And if we were to follow our units, so if we were to actually do this division here to check the units, we know that 0.10 is moles squared. So this would be moles per liter per second times 1 over moles per liter squared, which means that we could simplify this down, and this unit for K would be 1 over seconds times moles per liter. And again, the units here don't really matter in terms of what this number represents. These units here are just to make sure that the units in our overall equation balance out like so. In the next video, we'll look at rate law calculations and determining the relationship between concentration and reaction rate in chemical reactions that have more than a single reactant.